So here's a, other than, as I said, using a calculator or a computer program to find the area, here's the other reason why we need a numerical way to do this if we couldn't find the area using an antiderivative. Okay. For example, I don't know of any antiderivative for, well, any of these. Those look deceptively simple, yet go and try to find the antiderivative. It would be very difficult, and I can't think of one that would actually get me there. So there are a lot of functions that look very simple, but don't actually have an antiderivative for us, right? So when we want to find the area under those curves, like for example, let me just see if I've got, all right, so I'm going to bring up the picture. So that one graph that was y equals square root x times cos x, like there's the picture. There's clearly area underneath that curve, yet we can't find it with an antiderivative. So how can we do this if we didn't know it? Well, we're going to start with something a little easier and more familiar than square root x cos x. We're just going to take a look, well, maybe not, but I think this is an absolute value sine x graph. But here's how we're going to do this, okay? We're going to use the first rule, which is known as the trapezoid rule. And basically what I'm going to do is try to put trapezoids underneath this curve. So to start this one out, I'm going to use 8 trapezoids, and I'm just going to start by drawing it, and hopefully you'll see where the name comes from. First of all, does anybody know what a trapezoid looks like?
It's half of a hexagon.
Possibly. Yeah, so 2 sides are parallel. It's a 4-sided figure. So these are all trapezoid. Well, that one looks more like a triangle, but so will this one. But these middle pieces here look most like a trapezoid. And that's what I'm going to use because there's a nice simple area formula for a trapezoid. So I'm going to use these. Yeah, I'm going to use these to try to estimate the actual area under the curve. So if I was to go and draw these pieces, this is the error. I'll try to show you. This stuff here, because it's missing from the curve, there's going to be some error, right? It's not going to be quite big enough for what I'm trying to do, but it's going to be pretty close. So we can use this method to figure out approximately what the area is. And if we want a better estimate, well, we need more trapezoids. I promise there are no limits here, though. I promise we won't do any limits. But to figure out the area, well, first of all, we need to know how wide each piece is. So each piece here is delta x, because we use the same size every time we step along. Right now, there's from -8 to +8, so 8 minus -8 over 8 rectangles, so 16 over 8. There would be 2. And as we did it before, that was the same as the endpoints divided by the number of rectangles you wanted. Okay. So that's how we figure out how wide each trapezoid is, because we might want to do this for 1,000 rectangles, right, or trapezoids. Don't worry, in practice you would never do this by hand. 1,000, you would most likely have a computer to do it for you. But people would do it this way in practice. They would pick a number like 1,000 or something maybe more appropriate, figuring out, depending on how much, do we need to the moon accuracy or just enough to get by? So here we've got the width now of the trapezoid. We also need to figure out the height that we can use. And if you don't know the formula, this is basically the way it works is there's like a triangle here at the top. So I'm going to turn this into a square by 1/2 the base times the height, right? And add it to this other rectangle here. The way you can think about it is you basically are taking the average height. You're using that triangle up here to fill the rest of the triangle, and you end up with a height marked by this green line, which is halfway between the, how did that happen? Halfway between the top and the bottom. So the average of the 2 endpoints, if I called this, let's call this f of x1, and this would be f of x2, then the average of the 2 points would look like this. So for any trapezoid, if I want the area, it's going to be the height, which is here, divided by its width, or sorry, times its width. So width times height would be the average height times its width, and the width for each piece is b minus a over n. And what we'd have to do is add this up for every trapezoid. But the nice thing is that we can simplify it pretty easily. So let me show you how this would look. The first thing is every piece has the same delta x. So I'm going to factor that out. Here it is factored out. Okay. Then every piece has a fraction that is divided by 2. So we'll factor that 2 out as well, which means I end up with this now in front. Now all my fractions disappeared, and all I have to do is figure out how many times to add up the function. So if you look at the picture, here's how you get the formula. How many points did I need to make eight trapezoids? How many points did I need? Yeah, you're right. How many? 9. Because you can count them out here. There's a left side, a right side, and as I keep adding them up, there's actually going to be a total of 9 points here. And when I'm looking for this formula, you'll see that the endpoints, which are these ones, the first and the last one, they're only part of the first and last trapezoid. So like this point, oops, that's not a pen. So like this point and this point only appear on the last trapezoids, first and last. But this one, for example, it appears as the right side in one of them and the left side in another. So because it appears twice, like for example, it appears twice, every other point will happen 2 times except the first and the last. So instead of having to add them up every single time, you put a 2 in front of every function except for the first and last. Okay. So this is the sequence of the formula that we can use to approximate it. The more trapezoids we use, the more accurate it's going to get. Now, there is a way to do some of this in the TI-83. I'll give you a couple of options. Option number 1, which is easiest, is to go and get a program from the internet. I'll tell you right now that the AP exam does not require that you clear the memory of your calculator. That being said, they know the programs are out there. It's not really going to be to your advantage to have it there, but some people are like, the day before the exam, they've got they spent all night downloading programs to get ready for the exam. It might help you, but reality is you need to know how to do this without the program and the calculator. But you could Google for it. There's a port on the calculator that'll let you download a program.
That's what it's for.
Yeah. Anyways, the other thing is there are some built-in ways to do it. And my experience is that if you want to know the built-in way, I'll tell you this right now. The built-in way without programming the calculator is really only worthwhile for like big numbers, like maybe 20 or more points. It's better to just do it by hand for most of the things we're going to do. So I'm just going to show you what I had for instructions and tell you that if you'd like to know what your TI-83 can do, then come and see me after the lesson and I will show you the steps. But again, the steps, there are many, are only worth it if I was to ask you to, and I won't, do this for like 50 trapezoids or 100 trapezoids. Okay, but the TI-83 is capable. It just takes quite a bit of keystrokes to get it to do this. Okay, so we'll try approximating this area just to show you how the trapezoid rule works. It is not a very, it's harder to do what we just did. It's usually easier to try this. So let's figure out what's delta x going to be. If I want to start with 4 rectangles, and I'm going from 0 to pi, what will delta x be? Sorry? Pi over 4, yeah. So there's my delta x. And remember, because I'm using the points twice, because I'm averaging out the height, there's that divide by 2. So this is the part of the formula I'm building up right now, this one here. So it's going to be pi over 8 that appears in the front. It's going to be first point minus last point divided by 2 times the number of points. And we're going to evaluate it. We start at 0, so it'll be the sine of 0, plus 2 times the sine, and I move over by pi over 4. Plus 2 times the sine, I move over again by pi over 4, so it'd be 2 pi over 4, 2 sine 3 pi over 4, and the last one is when I land on pi. So remember, for these points here, the first and the last, they only occur one time as the endpoints for the first and last trapezoid. Everybody else appears twice. That's why there's a 2 in front of everybody else. So if I wanted to work out what this would be, I need a calculator at this point to punch the stuff in. So we'll go ahead and do that. Anyway, so in my calculator, I end up with my approximation is about 1.896 using the trapezoid rule. Okay. Now I'm going to have you guys try this one. See if you can follow the pattern. Try using it for 8. And again, I'm not going to make us go through all those keystrokes for the TI-83 unless you should choose to, unless you're curious about it, how your TI-83 would do this for you. So try it again. This time use 8 trapezoids to build up your approximation. So, oh, it should be more than 0 point something. But here's how it would be written out. This time our delta x is going to be different. It's going to be pi minus 0 divided by 8 rectangles. So each one moves over pi over 8. So we get pi over 2 times 8. And all the values, this is perfectly acceptable for you to do this in your homework so that you don't have to write it all out. If it's a small number like 4, you might as well write it out. But I'll know what you mean, and so would your AP examiners if you were to go like this and say, let me just make this one 2 pi over 8. Dot, 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 plus 2 sine 7 pi over 8 plus sine pi. So I'm running out of room here.
Sorry, did you say that is allowed or is allowed?
That would be fine. That you show the pattern just keeps going until here. You just have to show where the last term in your pattern is so that they know where the pattern stops. So if I was to add all those together, maybe someone can reconfirm this in case I punched it in the calculator wrong, but I had 1.974. Is that? Well, the true value is, we'll find the true value out later. I'll just give you guys a bit of a hint if you're a calculator junkie and you wanted to know about a little bit about it. Basically what you're having to do is go sum a sequence, and in this case the sequence would have been the sine of pi x over 8 from 0 to 8. That'll do everybody once, but then we also have to add to it all the middle people go twice, so we have to add them in a second time. So this would give you those values without having to punch them into the calculator, and it would work. Obviously we'd have to change. If you wanted 100, then those 8s would become hundreds in this example. But the people, oops, there's supposed to be an x here if you do it in your TI-83. It would go from 1 to 7. Those are all the middle ones.
There's already an x there.
So this is just a hint as to how you could calculate the middle part. That would calculate all these pieces right here. Okay, that's what it would do. It would add up all those pieces this way. And again, it's probably not worth it unless you have quite a few points. Okay. So you don't need to do that. As I said, I find it's harder to do it that way than to just punch it in the calculator. Okay, so if you think about what the trapezoid rule is doing, I'm going to go back to the picture just to show you what it's trying to do. And I'll have to zoom in on this curve a little bit so that we can...
F of x there, or it looks like a bunch of dots.
So this is what the trapezoid rule is doing, is it's taking a curve. So the black line would have been the curve, and it's trying to turn it into a line. So basically what it did is it said approximate the curve by this piece. And so somebody came along and they said, we can do better than using a line to approximate a curve. Why don't we use a curve to approximate a curve? So that person was Simpson, not as in Homer, but he was did quite a bit of this numerical approximation stuff. And basically what he decided to do was, instead of using a line, he put a parabola through the points. And, you know, I got to be pretty clever about using a parabola and not getting this ridiculous algebraic monster coming out. He was able to get a pretty simple situation here, which is, this is the formula he came out with. And the formula that he has uses the exact same amount of operations as the trapezoid rule. You see, the same number are multiplied. Everybody in the middle gets an extra multiplication. And there's still the same fraction, except a parabola uses 3 points, whereas a line uses 2. That's why there's a divide by 3 now instead of a divide by 2. So anyways, it would take a computer just as fast to do Simpson's rule as it would the trapezoid rule, which is why there's going to be some advantage here. It doesn't take any more steps, but it's much more accurate because we approximate a curve with a curve.
What's with the alternating 4s and 2s?
Yeah, well, that's part of the way it was derived. What I would suggest that you remember about this pattern is that odd numbers like 1, 3, 5, 7, those are going to be multiplied by a 4. The even numbers are going to be multiplied by a 2. And this has to do with the fact that when it was being interpolated, when we fit those 3 points through a parabola, then this is the way that the simplification ended up. And I don't want to make it any more complicated than that because really we just want to be able to use the formula for this, for Simpson's rule. Yeah, no, we won't be doing a proof for that. So, Simpson's rule, if we wanted to do on the same one we just did, Simpson's rule, I'll walk you through it. This time it's going to be b minus a over 3, and we're using 4 rectangles. So here's the coefficient in front this time. And remember, the first and the last piece are only used one time. Everybody in the middle goes 4, 2, 4, 2, 4, 2. Just 1 second, Anthony, okay? So to put the points in here, I would start at the sign of 0, add 4, the sign of pi over 4, then it would be a 2, and then another 4, and then the last one, which is the sign of pi. So if we were to put this in the calculator, tell me what the approximation is now. So I ended up getting, with just using 4 of Simpson's rule, I ended up getting 2.0046, we'll round it at. If you're trying to picture what Simpson's rectangle looks like, it would look something like this, where instead of having a straight line, there would be a parabola that would fit through the top of it. Okay? So, if we actually were to do this with the antiderivative and compare it to Simpson's rule and the trapezoid rule, this would be the negative of cos x from 0 to pi, which would be the negative of negative 1, take away the negative of 1, so all this together would be a 2. So the actual, exact value that we could do this on would be 2. And you'll notice that Simpson's rule got much closer with only 4 rectangles than the trapezoid rule could even with 8. So usually we'd prefer to use Simpson's rule, but the good news for everybody here that you need to hear is Simpson's rule is a part of our curriculum, but the AP exam only uses the trapezoid rule. So the trapezoid rule is the only one that you'll be expected to memorize for the AP exam. Okay? But Simpson's rule is, well, it's just less formulas to know, right? Less things to keep in mind. So the last thing I'll have you try here is we will do this one here. I would put this in your calculator as y1 so that you can evaluate it in your calculator as y1 of, for example, the first point will be at 0. That way you don't have to keep writing square root 1 plus and then whatever squared. You can keep referring to it in the TI-83. Okay, so try doing this with the TI-83. Why don't we just go, how about this? We'll share this out. This row here, I'm going to come back and ask you guys to do the trapezoid rule, okay? This row here, I'm going to come back and ask you guys to do the Simpson's rule. Others of you, you can copy it out as we have this. Okay, so I'm just going to write up the formula for you. I'm going to ask somebody to have calculated it, as I mentioned, in your respective rows. Oops, and of course that's still y1. So this is how I'd be entering it in my calculator. But I'm going all the way up. I'm going all the way up to y1. Okay, so somebody... Well, because remember in the trapezoid rule, everybody in the middle is used twice. So these are all the middle points. They all occur twice. Only the first and last point happen a single time. So somebody who worked it out in a calculator? Y1, what you do is, once it's in there, you hit the vars button. Yeah, variables. And then you go over until you see y variables. And then you pick y1 as a choice. Yes? Oh, right. Sorry, I forgot a 2 here. Thank you. Sorry. So, did we have a trapezoid rule approximation? Okay, so EJ, what was your approximation to this? 1487? Okay, 1 point. Try this again. 1.1. Keep going. That's enough. Okay. Simpson's rule. If you were to write this out using Simpson's rule, very similar. This time I'm using a 3 because I use the points 3 times to make my parabola. And the pattern looks like this. 4. 2. And it would keep alternating 4, 2, 4, 2 until I got to the last point where I would get 4 y1 of 7, 8 plus the last point. So remember the pattern again is that it goes 4, 2, 4, 2, all the way down. So what did we get for the approximation this time? 1.6283. That seems a little bit. See, this is the tricky part. This is the tricky part, right? You miss a bracket or you miss something, and it should be closer to this number here. 1.22. That seems a little large too. See, this is probably why they use a computer to do these calculations, eh? Did anybody get? It should be close to 1.14. I got 1.31. Okay, maybe I'll pause it then. So that seems to be working a little better. I think this would have been our 1.14779 and going. Now remember, there is a way for the TI-83 as well, which was the other thing I asked you to do. So really quickly, if we use the TI-83, you go to your graph and second function calculate, enter in your bounds, and I end up with my TI-83 says 1.1477936. So, I mean, we did pretty good here with only 8 of Simpson's rectangles. Yeah, we did okay. We made it to about there with the trapezoid rule. Okay. So, again, trapezoid rule, you definitely need to know trapezoid rule in order to do the AP exam. But the Simpson's rule is just part of our local calculus curriculum. Okay.